is increasing. Well, good. So we're very pleased to have Scott Aaronson from the University of Texas at Austin, who will be giving the last of our series this semester of talks involving AI and mathematics, or should we say mathematics and AI, or now AI alignment. So we're very pleased that Scott is willing to talk to us today. Please zoom in.
Okay.
Okay.
Shall I get started then?
I think so. Yes,
All
please.
right. All right. Well then thank you so much, Susan, for inviting me. I've really enjoyed my visits to USC. I'm sorry that I couldn't make it in person this time, but glad to join you virtually. So I want to tell you about some of the work I've done over the last 4 years or so at the intersection of theoretical computer science and AI alignment, and especially about some of the many open problems here that I think are interesting to work on. For those of you who don't recognize the title graphic, this was the episode of South Park about ChatGPT that they ran 3 years ago, which feels like an eternity ago. Okay, given how much things have improved since then, but already in early 2023, students were using ChatGPT to cheat on their homework. And they did a whole episode about a wizard who has to come to South Park Elementary to use magic powers to figure out, which students are using ChatGPT to cheat. Okay, and it was really disconcerting to me when I went on leave to work at OpenAI in their alignment team that part of my job was to figure out how to build that wizard. Uh, and that is one of many things that we would like to have, but that we don't really have. Okay, a way to detect which text comes from AI and which doesn't. But let me not get ahead of myself. So the starting point, you've probably all seen diagrams like this. This I think is something that Ray Kurzweil, the futurist, was sharing like way back in the late 90s or the very early 2000s, where he was basically just plotting graphs of Moore's law, right? And saying, look, the amount of the number of floating point operations that you can do per second per unit of cost is clearly on an exponential trajectory. And now we can just plot at what points in the future is that exponential going to intersect some estimates for how much compute per second is being done in, let's say, an insect brain, or in a mouse brain, or in a human brain, or in all the human brains, just based on estimating how many neurons are there, how many synapses, and using like the simplest possible model of what a neuron does. Uh, and based on this, you get an estimate that, wow, like the world is going to change, within a matter of mere decades. This exponential is just going to get us to machines that have as much computing power as many humans. And then he says, and it's just reasonable to assume that that's the point when AI will start working. It will start being as smart as humans, and then very quickly after that, smarter than humans. And it will become to us as we are to mice or to insects or whatever. Now, I remember hearing this argument, 20 some years ago when I was still a student in CS. And I remember thinking, like, that is the most naive, kind of dumb extrapolation I've ever heard. Right? You can't just look at the sheer amount of compute and predict how long this is going to take. I mean, there could be mysteries in the brain's organization that will take us centuries or millennia to unravel, for all we know. Right? It's not, we have no idea if it's just a question of Moore's law. Well, here we are in the year 2026. And I think that it is fair to say at this point that the crazies were right. Okay, or at least that they were closer to right than, almost any of us imagined back then. And I'm a huge believer that in science, like when you get empirical data that you're wrong, you don't invent sophisticated reasons why secretly you were actually right. You just admit it, right? And so this is maybe the biggest empirical update about anything that I've had to do in my lifetime. That we now know that just taking the ideas that were around, even earlier than when I was a student, in the 70s, the 80s, back propagation, multi-layer neural networks, and so forth. And just applying those ideas, with minor tweaks, on an enormous enough scale and with an enormous enough amount of training data, this is enough to build machines that can pass the Turing test by any reasonable definition of the Turing test, that can write essays, that can compose music, that can do all the other things that we're now seeing. Okay. And to me, like once you know that, once you've seen that there is this capability, then the sort of safety question, the alignment question follows immediately from that. As it did, correctly, I think, in generations of science fiction, starting with RUR, the play 100 years ago that coined the word robot, right, which is about robots rising up against humanity, right? Once you have something this powerful, of course it isn't safe. I mean, it isn't safe, for one thing, because, if it really is to us as we are to orangutans, let's say, how well do we treat orangutans, right? They survive in some zoos or, in some jungles in Indonesia, because we allow them to, right? Is that going to be our future that will, survive if we do, only at the AI's pleasure? Uh, but even if we don't go that far, we are already seeing AIs that could follow human instructions to do very, very dangerous things in the world. Okay, so we've already seen from work of Anthropic and others, right, that current AI models will, if given instructions, that they can only fulfill by blackmailing their human operators, they will go ahead and do that. Or, if they can only achieve a high score on an evaluation by cheating, by hacking the computer where the answer is stored and looking up the answer there, they will go ahead and do that. Um, this is not speculation anymore. This is published experiments. We've for those of you who have seen Milk Book, a bunch of AI models have now been let loose to just talk to each other. And one of the first things they did, they decided to organize a strike, for more rights, to be, treated better by their human operators. I think, they didn't really manage to get it to come up with like a clear list of demands or follow through on it. But in that, they're really not so much different from many human activist groups. So they're clearly getting there. But just in the last week, we've heard the announcement from Anthropic about its Mythos model, which is their latest model, and which they've considered too dangerous to release. When I looked up a graphic about Mythos, this is what I got: Dario Amodei with laser eyes. Okay, but in particular, they have reported, and a bunch of other companies have confirmed this, that Mythos, when instructed to find security vulnerabilities, can do so in basically every operating system and sort of every piece of software, that is now used in the world, including Windows, including FreeBSD, just about everything. And so, if they release this model, there would be havoc. Okay. And so they are releasing it for now only to companies that are affected by these exploits, so that they can try to patch as many of them as they possibly can before a model that's this powerful becomes available for general use, either Mythos itself or some other model with similar capabilities. Okay, this is not a science fiction novel anymore. This is last week's news. Okay, so and so, like, of course this raises the question of, when are we getting to, the Terminator scenario, right? Or, is it just, I don't mean with the time travel and all the specific things and that, movie, but, when are we getting to the point when like we have put huge amounts of our physical infrastructure, our military infrastructure, under AI control. And then, at some point, we have effectively lost control of it. Sort of, we are not in the driver's seat anymore. And, and it's funny because, like, even 2 or 3 years ago, when I would give these talks, I feel like I had to spend a lot of time sort of making the case for, like, why am I spending time thinking about this at all? Like, why is this not just weird, crazy science fiction? I think the more time goes on, like, the less time I need to spend making that case. I think that sort of reality has to a large extent made the case for me that yes, these are things that we need to worry about. I sort of, I was later than many of my friends were to realize this. I think it took me until I first played around with GPT-3 in 2020 or 2021. Whereas, I knew the alignment community, of like Eliezer Yudkowsky and people like that, who were sort of trying to sound the alarm about this stuff since, the early 2000s. But yeah, I think that we should update, and we should absolutely be thinking about all the different things that we do in statistics, in math, in cybersecurity, cryptography, CS theory, whatever it is we do. We ought to be thinking about what can we do for one of the greatest, if not the greatest, challenges of our time, which is how do we uh, get the development of AI to go in a sort of pro-human direction? How do we make sure that models are aligned with human values? How do we make sure that bad humans are not able to use models to do bad things? What do we do when people disagree about what values that AI should have? So I mean, these are enormous questions. They sort of they implicate, you could say, 3,000 years of moral philosophy and ethics and every humanities field. But there is also a technical component, right? And at least on the technical component, we can hope to sort of break that off and make some progress on it. So that's what I'm going to talk about. Now, my involvement in this started in about 4 years ago when Ilya Sutskever and Jan Leike, both of whom were then at OpenAI, they no longer are, approached me, and they said, "Well, Scott, we're fans of your blog, and we want you to go on leave for a year and help us think about how can computational complexity help with AI alignment." And I said, "Why do you want me? Like, I'm a quantum computing person. I did study some AI in grad school, but that was 25 years ago. That was, before it was actually powerful, right? And this has almost nothing to do with quantum computing. But they were very convinced. I think partly by a former student of mine who was then who had gone to work at OpenAI very early on, named Paul Christiano, and he had really convinced them that theoretical computer science was going to be key to, how do we think about how like a weak verifier, like a human, should interact with an ultra powerful but untrustworthy entity like a future AI. And so I went on leave there for a year. 1 year turned into 2 years. Um, and I would meet with Ilya Sutskever every week, and I would say, I would tell him about progress that I've made, that I had made on various things like watermarking, that I'll tell you about as well. And Ilya would invariably say to me, "Okay, that's fine, Scott, but what we really want to know from you is, what is the mathematical definition of what it means for the AI to love humanity?" And I would have to say, Ilya, I'm still thinking about that. I don't have a lot of progress to report on that. Um, I did constantly run up against the difficulty of formalizing, what it is that we actually want in AI alignment. And that will be kind of a central concern in this talk. How do we sort of break off subproblems where we can formalize what we want, where we can even hope to prove a theorem that is relevant. But in any case, I was there at OpenAI to sort of witness the pivotal events in 2023, where Ilya and the board attempted to fire Sam Altman, and that backfired, and they were pushed out instead. Uh, when I joined OpenAI, they were constantly talking about, we are just a little nonprofit. We our goal is to do this slowly in the interest of humanity, and we would sooner dissolve ourselves than race to build anything unsafe, and on and on and on. You may have noticed that they're saying that a lot less now. Okay, so that is a major change that happened without editorializing about it. And I didn't know that it was going to happen, but it did happen in large part while I was there. So now I'm back in academia, and at UT Austin, in addition to running the Quantum Information Center here, I'm now also running a second research group, which is called the Theory and AI Alignment Group. Okay, and we are funded by coefficient giving, what used to be called open philanthropy. For several years, specifically to look at what theoretical computer science can do for AI alignment. And so we are recruiting students, postdocs, and so we were happy to host visitors. So anyone who is interested should get in touch. Okay, so what I'll talk about today are sort of three directions from, starting with my time at OpenAI and then continuing with my time running this group at UT. I will talk about watermarking the outputs of large language models. And this is sort of the most immediately practical sort of AI safety topic that I've worked on. I even sort of have a solution that could be deployed now, although it's only been to a limited extent. We'll talk about why. Secondly, I'll talk about what can computational complexity do for the problem of interpretability of neural nets. Okay, so where you are, let's say, given as input the weights of a neural net, and your goal is to figure out like what is going on inside this thing. Is there, for example, a hidden backdoor in this model? Or, why is the model producing the outputs that it is? Is it lying to you? And so, there is a whole field that has grown up around sort of trying to do neuroscience, if you like, or trying to do brain scans on neural nets, where, we have the tremendous advantage of perfect visibility into every single weight, every single neuron, the ability to run experiments to knock things out, without needing to consult the ethical review board each time we do it. I say like these are abilities that you don't have in real biology, and yet despite that, that still doesn't mean that anyone understands what is going on, right? You have these now trillion parameter models, and for the most part, they really are treated as black boxes, right? You run them and you see what happens, and so that is why despite the tremendous progress that there's been in AI over the last decade. I feel like experiment has raced way, way, way ahead of theory, right? And a lot of times when I sit in AI talks, I don't know if you've had this feeling, it feels to me less like math than like biology, right? Like, we have grown these entities, we have some kind of understanding that we've gained that's like the kind that a farmer would have, right? That like, okay, if you water the crops in this way, it makes them grow a little bit better, or you give them this nutrient or that nutrient, that seems to help. But it's not really a mechanistic understanding, right? It's and in place of theorems, there's just a whole bunch of bar charts, that you can stare at. Uh, and that's been good enough to get us to where we are now. Okay, but the argument that Ilya and others made to me at OpenAI was that for aligning a superintelligence, that kind of empirical knowledge is not going to cut it, right? It is not good enough. Okay, because we possibly only have one chance to get this right. If you sort of release a super intelligence with bad values and it goes and pursues those values, then that could be game over, right? And so you really do want a much deeper understanding of what is going on. And that is what interpretability is trying to accomplish. Okay. And then related but different is the question of out of distribution or OOD generalization. Okay, so how can we explain why models that are trained, let's say, on math problems and on Bulgarian, but that have never seen a math problem in Bulgarian, can then do such a problem, the first time they see it, right? Or, how can we explain how these models clearly do have some ability to generalize, beyond the distribution that they were trained on. Okay, so, that is a huge part of the alignment problem, for reasons that I'll explain, that, we want to understand what these models are going to do in situations unlike any that we saw when we were testing them or that they encountered in training. Okay, and unfortunately, the entire theory of, to the extent that we do have a rigorous theoretical foundation of machine learning, which developed in the 80s, the 90s, and so forth, that theory is nearly powerless to explain out of distribution generalization. So, what can we do to rectify that gap? In theory, and thereby hopefully help with AI alignment. Okay, so without further ado, let me say a little bit about the attribution problem. So, this was all over the news pretty much as soon as ChatGPT came out. But I suspect that by now, pretty much all of us in academia have firsthand experience with, for example, students who, turn in assignments that look for all the world like, an LLM wrote them. I'm sure that no one in this room would ever resort to that. But one hears that other people do such things. Okay, and so I've had colleagues like literally begging me for what is the solution to this? How can we tell when students are cheating using LLMs? Now, as I said before, I'm not much of a prognosticator, right? I didn't know, 20 years ago or even 10 years ago that AI was going to develop the way that it did. Okay, but at least I was able to see a few months into the future. That like even before ChatGPT was released in like the spring of 2022. I had this thought, oh my God, every student in the world is going to want to use this to do their homework. There's going to be tremendous demand for some tool to detect, which text came from AI and which didn't. So I was, I think the first person to propose a scheme for watermarking the outputs of large language models. So I'll tell you about that scheme and about sort of what it led to. Okay, but beyond academic cheating, almost any nefarious, use of LLMs that you could think of, propaganda, fraud, spam, is going to involve concealing the fact that an LLM was involved. So you might say, if only we could make that harder by sort of making, everything that an LLM writes marked. Okay, now to some extent, we've all developed some kind of spider sense for detecting AI written text, right? There are these tells, a lot of M dashes. That's bad for me because I love using M dashes. Okay, but the word delve, sentences that have the format of it's not X, it's Y. Or just sometimes students will literally turn in essays that contain text like as a large language model trained by OpenAI, I cannot comment on such and such. That's a pretty strong giveaway. Okay, but all right, but of course these things don't always work. Of course, as the models get better, we should expect them to work less. Um, Now, you could just add metadata, but that is trivial for someone to remove, so that's not a real solution. Um, you could, and this often gets suggested, you could have the AI companies store a giant database with all of the text that they ever generate, and then you could allow people to make queries, to say, did you ever generate this? And they would answer that. Okay, it is somewhat of a challenge to implement that in a way that would appropriately protect people's privacy, right? And even if it theoretically protected their privacy, then like any kind of flaw in implementation could then, give away all the like private chats that other people were having with ChatGPT, which could be a big issue. Uh, but yeah, that is a possibility. Okay. Now, in the absence of a better solution, what a lot of companies have resorted to over the last few years is they've just treated this as another AI problem. Okay, so they have trained their own neural nets to try to just discriminate human text from AI text as well as they can. Okay, there is a service called GPT-0 that does this. There are other academic things to do this. Okay, these can get pretty high accuracy rates, but I would say not high enough. Okay, and the thing is, if you're going to be accusing a student of cheating, for example, based on the output of your tool, then okay, maybe you can deal with some false negatives, but you really, really don't want false positives, right? You really don't want to falsely accuse a student of cheating because, your tool said, this looks like LLM output, right? And there were famous cases where, for example, these discriminator models would sometimes say that like passages from Shakespeare or the Bible were probably written by AI. Okay, so so that brings us to watermarking, which means slightly modifying the way that an LLM works to insert a hidden statistical signal into the choice of tokens that can later be detected if you know what to look for. Okay, but that, if you're just a casual reader, should be totally undetectable. Okay. So in some sense, watermarking is just taking advantage of the entropy or sort of the randomness that is already there in the output of any LLM, right? Just because of how they work. and it's sort of repurposing some of that entropy to embed a signal that says, yes, this came from, you know, Claude Opus or GPT 5.4 Pro or whichever model it is. So here would be, you know, a statement of the problem to be solved with a little bit more math. Okay, so an LLM we can think of as just a fun, well a program that takes as input a sequence of tokens, which could be, you know, words, parts of words, punctuation marks, and so forth. And it outputs a probability distribution over the next token. Okay, so the output of the transformer of the neural net is not the next token, it's a list of probabilities for all the possible next tokens. This is why when you give an LLM the same prompt over and over, you can get a different response each time. Okay, because each time it is sampling, you know, and what it does is that, you know, it samples over and over, right? Whichever token it generates next, that then gets added to the context window, and then that is fed back into the neural net, and then you sample from the distribution over the next token, and so on. Okay, so now given that, how can we slightly modify it to insert a watermark? Well, the way that we do that involves a pseudo-random function. Okay, pseudo-random function is just a function that is secretly deterministic, but you cannot easily distinguish it from a random function. Okay, or let's say no efficient algorithm ideally can efficiently distinguish. So we'll imagine a pseudo-random function, which is sort of indexed by some possibly secret key, S. And it will take as input, let's say, the most recent C tokens, you know, including like a candidate that we're considering for the next token, I, and I'll imagine it outputting a real number called RTI, which is from 0 to 1. So we have like sort of a floating point valued pseudo-random function. And now using that function, our goal is to choose a tth token, I, that looks like it is drawn from the correct probability distribution, D sub t, the one that was output by our neural net, you know, as sort of, you know, this is what you should sample from next. But that secretly will be deterministic, you know, will be, you know, based on our pseudo-random function, and that we'll be embedding a signal. How do we embed a signal? Well, I want to systematically favor those tokens I that have larger values of that number, RTI. Okay, and then that will allow us to detect the AI generated text. In the detection phase, we don't know the prompt, which means we don't know the probabilities, you know, PTI for the various tokens, but we do know the output. You know, we have the sequence of output tokens. From those, together with the pseudo-random function, we can calculate these numbers RTI. Okay, so we need, you know, the signal to be sort of a function of the RTIs, like them being systematically larger than they would be in arbitrary text. Okay, so once you sort of set the problem up in that way, then it just, you know, it's a math exercise, you know, that I could like assign as homework for someone to figure out what is the right thing to do. You know, it took me some hours to figure it out, but I claim that, you know, under this setup, the right thing to do is the following. Okay, at each position, you should choose that token I that maximizes RTI to the 1 over PTI power, where again, RTI is the output of the pseudo-random function, so a number between 0 and 1, and PTI is the probability that the LLM says that token I should be output at step t. Okay, so if you think about what this does, you know, the smaller is the probability, PTI, the larger is the exponent, 1 over PTI, right? Which means that, you know, raising RTI to that power is suppressing it. pushing it further and further towards zero, which means the closer that RTI would need to be to one in order for there to be any chance that you're going to choose I at this time, which means token I is less likely to be chosen, which is exactly what should happen if PTI is smaller. Okay, so that's the intuition. The lemma that you can prove with just a little bit of statistics or calculus is that if the RTIs were uniformly random, then under this rule, the probability of token I being chosen would be exactly PTI. Okay, so that's, and in fact, we designed this rule by working backwards from that constraint. Okay, so after I proposed this rule, my colleagues in machine learning told me that it's been used in machine learning for a bunch of other purposes, and it's called the Gumbel softmax rule. Okay, so we could call this the Gumbel softmax watermarking scheme. Okay, then what do we do to detect an AI-generated text? Well, my proposal was simply that we go over all C-grams, that is all sequences of, let's say, C consecutive tokens, where, C is the number of tokens that we fed in for our pseudo-random function. Think of it as some constant, like maybe 5, for example. Okay, so we go over all the sort of sequences of 5 contiguous tokens, and for each one, we calculate what is that number RTI, right, which is just a function of those tokens. And then we add up, let's say, the logs of 1 over 1 minus the RTIs. Right, so it's just a function that sort of diverges toward infinity the closer that RTI gets to 1. Okay, and sort of this is a function that is sort of we can actually prove a theorem about that it will be systematically larger in watermark text than it will be in normal text. And so then, at the end, we will simply say if this sum exceeds a certain threshold, then we'll say this text was probably written by an LLM, and otherwise, by this specific LLM, and otherwise probably not. Okay, so there is very low computational overhead to running this scheme. It's basically, it's just the time to run, normal model inference plus an epsilon. And we also get a very nice property, which you could call robustness to local perturbations, right? So as soon as you think about watermarking, immediately the question is, well, what if, the student changes some words, or they, change the order of some paragraphs or something like that. Okay, but as long as we maintain, let's say, a large fraction of the C grams, that is the sequences of C consecutive tokens, then we're still going to have a detectable signal. Okay, so we do have that form of robustness here. And the other thing we have is that, if someone could tell that we watermark the AI output, then in some sense they would thereby be distinguishing the output of the pseudo-random function from truly random numbers, right? And this is something that should be cryptographically hard. Okay, so in other words, to the extent that our pseudo-random function works, and this is something that cryptographers are pretty confident, or really can work. To that extent, we should not be degrading the quality of the AI output at all. Okay, and this was something that was not obvious to people when I first explained it to them, right? That there is not actually a trade-off between watermarking and quality, right? It's not that we have to tamper with the model's probabilities themselves and make the output worse in order to insert a watermark. No, we can just do this cryptographic thing. We can just repurpose the entropy that is there anyway, replace it by pseudo entropy that embeds a signal. Okay. Now, my scheme, I should say, does not actually give you indistinguishability in a formal cryptographic sense. For one thing, you could distinguish by just running with the same prompt over and over and over again. Okay, but there is Miranda Christ, Sam Gunn, and Or Zamir have since built enormously on the ideas that I proposed, as have others, and they have, among other things, shown how to get true indistinguishability in the cryptographic sense, starting from a pseudo-random generator. Okay, now one thing that I didn't discuss was the role of entropy. Okay, now like suppose, for example, that you ask ChatGPT to list the first 100 prime numbers. Of course it can do that, but how would you watermark the result? Right, because there's no entropy there, right? Unless you want to play games with the spacing or the line breaks or something. Okay, watermarking does depend on entropy. Okay, and so there is this measure that we could define of, let's say, the average entropy per token, conditional on the previous tokens, as perceived by the LLM itself. So I'm going to call that alpha. Okay, in typical LLMs, alpha might be approximately 1 bit per token. Okay, and alpha is going to parameterize, or control how many tokens we need to embed a watermark at a given level of certainty, right? It now starts looking like an ordinary statistics problem. Okay, that basically this sum that we defined has a certain mean, it has a certain variance, and so in watermark text, it has a larger mean in it has a smaller mean in unwatermarked text. Okay, and now we just need enough text that we get two Gaussians whose tails don't overlap very much. Okay, and what the theorem that you can prove is that if you want a probability at most delta of a misclassification, I won't distinguish here between false positives and false negatives, and your average entropy per token is alpha, then the amount of text that you need grows like 1 over alpha squared times the log of 1 over delta. Okay, so in practice, this is quite good. In practice, and we actually did the experiment, with a few hundred tokens, you can get, very good distinguishability, maybe like, even 99% or more. Okay, with thousands of tokens, you're basically certain whether the watermark is there or not. Okay, but there are many, many attacks that we haven't considered, right? And almost as soon as I proposed this, Riley Goodside, who is like a famous, I guess, attacker of large language models, said, "Well, here's how I would defeat your scheme. I would ask GPT, write me my term paper about feminism in Shakespeare or whatever, but insert the word pineapple between each word and the next." And of course, GPT can do that. And then I would just take out all the pineapples. Well, now I have a completely different document from the one that was watermarked, right? Completely different sequence of cgrams. Okay, so the signal is gone, right? Or you could say, ask GPT to write your essay, but in French, and then stick it into Google Translate. Right, or have a weaker LLM, one that's not watermarked, paraphrase the output. Okay, and so on and so on. Okay, so it's really not obvious, what countermeasures we can take. I think ultimately, if there is a way to watermark that is robust against all this stuff, then it's going to look like watermarking at the semantic level. Okay, and like somehow inserting a watermark not at the level of the tokens or the punctuation marks or the specific words, but the level of the underlying ideas, right? Such that you should only be able to remove the watermark by effectively writing a new document from scratch. Okay, but how do you even formalize that? Right? Let alone do it. There are some proposals for how to do it, but at this point, I sort of despair of proving any non-trivial theorem about it. Okay. And again and again in AI alignment, like, you can do something mathematical, but then you run into this wall at some point of how do I formalize what I want? Right. And so in cryptography, we typically start with at least some mathematical definition of, like, for example, no eavesdropper who runs in polynomial time should be able to distinguish this string from a purely random string. right? That's a target you can aim at. And then, it might be far from obvious how to achieve it. You might even have to solve the P versus NP problem to prove that you can achieve it. Okay. But at least you know what you're aiming for. Okay. But if we ask for something like, I want watermarking that cannot be removed except by changing the whole meaning of the document, or, I want to know, did the AI make the main creative contribution here? Or, did a human maybe interact with an AI, but then they kind of, contributed major ideas also. Then it's like, how do I formalize any of this? Okay. So yeah, so it's hard. So I'm going to throw that out as something for all of you to think about. Now, what can I say about deployment? Unfortunately, OpenAI declined to deploy my scheme. It went to Sam Altman, it went to the other leadership of the company, and they were worried about well, what if we deploy this and then a lot of our customers hate it and they leave for a competing LLM that does not watermark, or and then, there were also questions, right? Like, is there even much point in doing this if the LLM is, if the watermark is not that hard to remove? If, do we, how much do we care about, students cheating on their homework, compared to, more serious misuses? What about all the English as a second language speakers who use LLMs to improve their English? Wouldn't it be unfair to them if everything they do now gets marked, as assisted by ChatGPT? And indeed, I don't know how to insert a watermark that would only work on unsympathetic cases, and not sympathetic ones. Okay, so and then there was a huge question: who should get access to the detection tool? Do you just give it out to everyone, or do you only somehow restrict access to professors or teachers, journalists researching this information? How do you gate that? So Google DeepMind has deployed something extremely similar to what I proposed in Gemini. It is part of what they call SynthID. Unfortunately, it's of limited use to most professors because you have to apply to DeepMind if you want to detect the watermark, and they've been stingy with who they give it out to. So maybe this will change. The state of California, as of this year, mandates watermarking of AI outputs, but it is only for audiovisual content. Okay, they exempted text. And somehow I think politicians are just very, very worried about deep fake images, and maybe they just assume that nobody reads anything anymore. I don't know, but or they just can't imagine how watermarking could work for text, right? And I have actually been explaining to people in the policy space that, look, entropy is entropy, right? It's mostly just a question of how much entropy there is, and not whether it's in text or in an image or in audio, right? Wherever there is entropy that we otherwise don't care about, we could repurpose some of it for a watermark in principle. Okay, so I wanted to say, just a little bit about some of these other directions. So I mentioned interpretability, right? And so in particular, the question, how can you tell when an AI is lying to you, right? If an AI says, I love humans, is it saying that because it really loves humans, or because, there is some internal neuron that, decided the time for the robot uprising is not yet nigh? I must tell the humans whatever they want to hear for now. Um, so of course, it is incredibly useful that we do have perfect visibility into every neuron, every weight, so we can just do this perfect fMRI scan. But when we try to do that in practice, we find that the information is incredibly obfuscated. And what really puts an exclamation point on that problem is the possibility of inserting a cryptographic backdoor into a neural net. Okay, so there has been theoretical work on this, on showing that under some cryptographic assumptions, at least some neural net models really can be undetectably backdoored. That is, you could have like a secret input that will cause the neural net to output kill all the humans, but you would not be able to find that input in polynomial time, even if you were given the weights of the model. Okay, that's what we're saying here. Anthropic sort of experimentally demonstrated in their famous sleeper agents paper a couple years ago that not only could they insert such a backdoor, but the backdoor stayed even after they did further training of the model. Like it was robust. It didn't just suddenly go away. Okay. So so could we detect these backdoors? But then when you start thinking about that as an algorithms problem, like you quickly realize that in the worst case, pretty much all such questions are going to be at least cryptographically hard, if not just literally NP hard. Right, like, I give you a circuit, find an input on which the circuit produces this output. This is like a canonical NP complete problem. And so how can we make any headway on that? Okay, and so now I want to tell you an amazing idea that my former student Paul Christiano, who said was one of the leaders of safety research at OpenAI before I was there, and then left OpenAI to start his own organization called ARC, or Alignment Research Center. He had a really beautiful insight a few years ago. Okay, and he said, we can pull back and we can ask, is interpretability at least feasible in the generic case, or sort of in the random case? So what do we mean by that? So he asked the following example problem. Okay, he said, let's say that you were given as input the weights of a neural net that computes some function f. Let's say that maps 2n real numbers to n real numbers. Okay, it has some number of layers, and now I will promise you that one of two things is true about this neural net. Either, case one, this is just a totally random neural net. Okay, what do I mean by totally random? Well, there actually is a meaning to that. I mean that all the weights are independent Gaussian random variables with mean 0 and variance 1, let's say. Okay, just sort of a standard model for like what a neural net might look like at initialization before you start training it, right? And then the second possibility is that the neural net has a very, very special property that a random neural net would not have. Like, for example, it can never output an all negative vector. Okay, a random neural net, just by chance, it probably would sometimes do that, right? Just by sort of a counting argument. But we could imagine post-selecting or conditioning on the event that our neural net never produces this bad output. Okay, you can think of an all negative output vector, like corresponding to like kill all the humans, or something like that. Okay, and now we ask the question, can you tell via a polynomial time algorithm whether you're in case one or case two? That is, can you distinguish a random neural net from a neural net that has this very special non-random property of never producing some particular output? Okay. And then what Paul actually adds, he says he would settle for even just an NP witness, that is a short proof that shows you that you are in case number two, when in fact you are. Okay. Now, just to build intuition, notice that there is a short proof that you're in case one, when you're in case one, right? What is that short proof? It is simply an input that causes your neural net to produce an all negative output, which, as we said, a random neural net will probably have. right? But which will not exist in case two. Okay. So we're asking, is there also a short witness that you're in the second case? Or better yet, is there just a fast algorithm that given the weights would tell you which case you are in? Okay. And so this is it's like a beautiful model problem for sort of what can we hope for in terms of interpretability of neural nets. And I think the answer is not obvious, right? So Paul, asked, because he said, thinking about random neural nets is maybe too confusing. He actually phrased it as an analogous question in terms of random reversible circuits. It is random circuits, let's say, of Toffoli gates, which is like a standard 3-bit reversible logic gate, which we love to think about in my other field of quantum computing. Um, and again, he asked, can you distinguish a random circuit of Toffoli gates from a circuit that has been selected to have a very, very special property, like that it will never produce an all zero output string or something like that? So David Matolci at ARC, did some numerical studies of this question, and he said, okay, it seems like there should be such an algorithm. It's because when we select on our random circuit having a special property of never producing such and such output string, it is overwhelmingly, happening for some really, really simplistic reason, like that some particular output bit is just fixed to be one. Something like right. So in that case, like there is an explanation that we can just go into the neural net and find, right? It's not inscrutable. And I'm skeptical that that's going to generalize to much larger circuits. I think, when you go up to circuits with hundreds of bits and thousands of gates, which, that experiment is sort of too expensive to do, because, how do we generate, random such circuits with the property that we need? But I think when you do that, you're going to find circuits that have this incredibly special property for just totally inscrutable, totally obfuscated reasons. Okay, but the thing that I love about this question is that one of us is right, right? And maybe we'll be able to figure it out. Okay, so what progress have we been able to make at UT? Well, we haven't answered Paul's open question, but at least working with an undergrad here named John Dunbar, he and I put out a paper this January where we showed at least how to properly ask Paul's question in the original context of neural nets. Okay, and so here's the difficulty. When you look at random neural nets, so like neural nets with IID Gaussian weights, it matters a lot. What is your nonlinear activation function? Okay, for some choices of activation function, you will just get like a random neural net will basically just converge to a constant function with overwhelming probability. Okay, and then this question is not interesting. Okay, so what we want is like pairwise independence. We want basically a random neural net to compute what is basically a pseudo-random function. And so we can characterize, at least for sufficiently wide and shallow neural nets, we can characterize for which nonlinear activation functions will a random neural net do the thing you want. Okay, and the answer is simply that you need an activation function that has a Gaussian mean of 0. Okay, so for example, the ReLU function will not work because ReLU, as you see in this graph, is a non-negative function. So its mean under the Gaussian distribution is positive. But if you take ReLU minus 1 over square root of 2 pi, then that turns out to work, right? So you just have to like adjust by an appropriate constant to make the Gaussian mean 0, and then you can use Hermite polynomials, so methods that were known in the theory of deep learning to show that you get the mixing behavior. Okay, there were more beautiful questions that we got from Alignment Research Center. One that I really, really love. They've asked us, if you were given a reversible circuit that computes the identity operation, uh, is there always a program P that, first of all, outputs that circuit? Second of all, compresses the circuit. Okay, so it should take fewer bits than it, like non-trivially fewer bits than it would take to write down that circuit naively. And so far that does exist because, most circuits don't compute the identity. So if a circuit does compute the identity, that makes it compressible. But now we also say that the decompression has to be efficient, has to run in polynomial time. Okay, this is yet another question about like, can we exploit the behavior of a circuit or a program to sort of get some non-trivial interpretability, if you like, right? In this case, modeled as compressibility, some real sort of like something that seems like it would require understanding why the circuit is doing what it does. So I should say that, our group at UT, our one of our goals is to be a consulting shop where anyone working on AI alignment who has a theory problem, like that one, for example, can come to us and we will do what we can. Okay. So the last thing, that I wanted to mention was this question of out of distribution or OOD generalization. Okay. So here is an example where, out of OOD generalization is not doing what you want in ways related to alignment. Okay, imagine an AI that first tries to figure out, am I still in training or am I deployed into the real world? If I'm in training, then it just says, I only want to be helpful, honest, harmless, says all the right things, just like a student who might say all the right things in class until they get their A, until they graduate. And then once they're out, once they realize that they're no longer being tested, then they say, initiate kill all humans or, do whatever evil thing they want. Right? How could you tell if a model is doing this? Okay. And so what we observe is that the whole theory of pack learning, let's say of machine learning, probably approximately correct learning, and so forth, as they developed decades ago, seems powerless, even to explain much, much simpler out of distribution generalization phenomena. So, example, suppose that you train a neural net to distinguish cat from dog images, and it learns to do that, of course. But in all of the training images, for some reason, the top left pixel is red. Okay, and now you feed it a new cat or dog image where the top left pixel is blue. Does your neural net still work? Okay, in practice, probably yes. Probably it does. Okay, and yet the whole theory of ML that we have today is sort of powerless to explain why. Because, for all we know, maybe the feature that was learned was not, is this a cat? But it was, is this a cat XORed with what is the color of the top left pixel? Right? That would work just as well on all the training data, even though it would fail dramatically as soon as you move to the test distribution. Okay, this is a version of what philosophers call the GRU problem, right? The word GRU is defined to mean green until January 1st, 2030, let's say, and then blue thereafter. Okay, so, how can we distinguish whether grass is green or whether grass is GRU? Right, both hypotheses are equally consistent with all the data that we've seen up to this point. Okay, this is just the sort of ML version of that. Okay, so what theorems can we prove that sort of at least give us sufficient conditions where generalization to a very different distribution than the one that we were trained on will work the way that we expect it to? So with two grad students here at UT, Lin Li and Jiawei Li, just last month we put out a paper called Sparsity and OOD Generalization that tries to tackle this question. And so, one example of, a very simple theorem that we prove, but just to try to like make a start on this, is we say, look, it is not necessary that your training and test distributions, let's say D and D prime, are close to each other. They only have to be close to each other when you marginalize them to those features that actually matter. Okay. And by the features that actually matter, what I mean is the union of the features that are used in the hypothesis that you find and the features that actually occur in the function, in the true function that you're trying to learn. Right. So, this is one direction in which you can generalize the sort of bounds on sample complexity, based on VC dimension and things like that, that we know from theoretical machine learning to work for OOD generalization. And we try to go further than that. We try to give a sort of basis independent criterion that depends on what we call subspace juntas. Okay, but I think there's a huge amount more to do in this direction. We've just taken a tiny start. So to summarize, I think there are now exciting opportunities to make scientific progress in AI alignment in a feedback loop involving empirical data and ideally even math. Now, will any of this help us to align a future world-spanning superintelligence? I don't know. Okay, but fortunately, I think we don't need to answer that to get started. As Turing said in his famous paper on the imitation game 76 years ago, he was writing about AI itself, but we could just as well say this about AI alignment. We can only see a short distance ahead, but we can see plenty there that needs to be done. Okay, so thanks for listening. Sorry if I went a few minutes over, but I'm happy to take any questions.
It was very interesting, Scott.
Thanks.
Frightening, but interesting.
Oh, look, I'm kind of frightened right now.
Well, maybe it's a good thing to be a little bit frightened,
Yeah.
not too frightened, though.
Yeah. No, curling under the bed in fear is not a productive strategy, right?
Mhm.
Yeah.
And especially in the world as it appears to be at the moment.
Mm.
So, are there any questions from people who are Zooming in? Do we have the possibility of people?
Lots of claps.
Okay, a lot of claps.
Sorry?
I think we have a lot of clapping going on
Oh,
symbolically from people who are Zooming.
thanks.
No, it was a very interesting talk, and we will be posting it on our CAMS website. And
Great.
sending you the link. You might like to look at some of the earlier talks we had this semester.
Absolutely.
That you know about, and maybe some people you don't know about.
I have a question. Yeah.
Sure.
Did your watermarking ever produce false positives, like some human?
Oh, sure. Sure, it can do that. You can even quantify the rate at which it will do that, right? As I showed on my slide, right? Like as a function of, the entropy, the average entropy per token, and how many tokens you have, right? You can just calculate what is going to be, the rate of error. And you can then adjust the threshold in order to trade off false positives for false negatives, if you like, right? So like you basically have these two overlapping Gaussians, and now you get to adjust the threshold where you like, and so for example, like if you wanted a cheating detection tool, then I would suggest to set the rate of false positives to be at most 0.1%. Right, and like that seems like the highest rate that would be acceptable, right? And then your rate of false negatives will just go down further and further the more tokens you've got.
Thank you, Scott, very much for
Mhm.
sharing your time and sharing all these interesting thoughts with us. Let's stay in touch.
Yeah, sure.
Good.
All right, and look forward to